Yeah, well, our next talk is held by Halvar.Flake about malware. I think he doesn't need too much introduction, so it's going to be a great talk. Enjoy.
1 second. Yay. Hi, good morning, my name's Halvar. I work for a company called Dynamics in Bochum, and I'm going to speak about structural malware classification. Essentially dealing with large quantities of malware variants in an automated manner. And I'll begin this talk by speaking a little bit about how hacking has changed in the last 20 years, and not always for the better. If we look at the history of it all, computer break-ins have changed in their structure. In the 80s and 90s, there were essentially 3 types of people you would meet on other systems. You'd have the classical hacker, which were people that were sitting at home and were just enthusiastic about technology and enthusiastic about other people's computers. Then you had the government types, which were fairly professional in their break-ins, and you had the classical virus authors. And the interesting thing about break-ins in the 80s and 90s is that almost all break-ins that you saw were not economically motivated, which means that the classical hackers wanted to break into something, get access, and use that to break into more things and get access. They didn't really care that much about making money. I mean, you had the occasional credit card fraud case, but really it was more about getting access and retaining access than it was about getting profit from it. Well, the spooks want nothing more than secrecy, really. They want to go into another system, exfiltrate information, and then, well, leave again. And the classical virus author was more concerned with his reputation amongst the virus writing community than he was about making money. He was primarily there for getting the fame associated with a particularly clever invention. Now, nowadays things look different. When I was young, the malware that you looked at was usually quite clever. Most of it was handwritten in assembly, and people put a tremendous effort into these little pieces of code. My personal favorites were the mutation engine MTE, which some guy in, was it Bulgaria, built back in the days. And most of what I know about Windows exception handling came from reading the Win32 source code, which, well, Win32 was the first virus to use exception handling to make sure that it doesn't crash while infecting. And then you had something like ZMist, which is probably the best metamorphic engine that has ever been publicly released into the wild, which was a full disassembler written in assembly that would take an executable, disassemble it, build all cross-references for it, then infect that executable, and then mutate the entire executable. The reason for this was that at the time, AV folks started looking for statistical patterns in binary, so they would sweep over a binary, and when they noticed, well, statistically deviant code at the end of it, they were like, hey, we have an infection. So in order to make sure that the code of the virus did not deviate from the code of the application itself, ZMist would just take the executable and morph it as a whole. So everything would look like garbage and not just the polymorphic stuff at the end. And, well, I hate to sound like an old dirtbag, but when I was younger, malware didn't suck quite as badly as it does now. In the sense that malware is no longer written for fun, and it's mostly written for economic motives, and that actually decreases quality to a certain extent, as people, well, they have to make money with these things. So, malware is created under economic constraints all of a sudden, and it's built under the most bang for the buck thing, which is interesting because malware development starts to resemble more and more regular development. So you have no more difficult to maintain assembly snippets, you have C++ code, you have a release cycle, and you release something, and you fix, or you notice an issue, and then you release an update, and so forth. And I'm quite sure that they have like proper development teams and development plans now. I mean, you see specific variants that behave differently targeted at events like Halloween or Thanksgiving, which means somewhere in Russia there's a team of people and they have like a big calendar and they're like, okay, this feature has to be in this worm by next week, right? So and I'm quite sure they have project managers and the like there now. So it's not what it used to be in that sense. Like it's real development, and that makes it kind of interesting. Now, the thing with AV is that antivirus it's a rather interesting industry. It's huge financially. I mean, I read some crazy statistics that 55% of all security spending within Europe goes to antivirus. And 55% of all security spending in Europe, that's a big chunk. Now, the amusing thing about antivirus is that technically, there hasn't been a whole lot of movement since the 80s. In essence, we're still wearing jackets with shoulder pads and long hair. What we have is still the byte-by-byte scanning engines underneath it all. We have many more signatures and a lot of rather amusing and trivial patents, but really nothing much has changed. We still have essentially a string of bytes with a bunch of wildcards, not even a full regular expression, just a string of bytes with a bunch of wildcards, and perhaps some extra instructions on where to look for what features. And these things get compiled into a big tree-like structure, and then you run over a gazillion files and look up, hey, is this exactly the byte sequence that we know? These signatures have two disadvantages. First of all, they're very brittle. What do I mean with brittle? They break very easily. Like a minor change will make the signature completely useless. And secondly, they're very localized. You're only running a signature over a very small portion of the executable. Now, this means that an attacker only has to change that small section of the executable and he can reuse 90% of his code. So if you have developers have cooked up 250,000 lines of code for your bot, you really just have to change one function, and you're right where you used to be. Now, extracting signatures from antivirus engines is really easy with a black box attack. Storage is really cheap these days, so you have your bot, you've just built it, and you notice, hey, the AV guys are starting to add signatures to the engines, and you would like to know, what do I need to change? So what you do is you take a file, and let's say it's got a size of like 70K. Now you make 70,000 copies of it, flipping one byte at a time in that file, and scan it again. And now the AV will flag 69,500 something of these files as infected, and a few of them as not. And yay, you have just isolated those bytes that are responsible for identifying this thing as bad. And what you do then is you look at your debug symbols. You have the source code, so you have the debugging symbols, and you get a list of functions that you need to recompile with different compilation options, and then release the bot again. So this entire process of offline polymorphism can be automated in that sense, and I'm actually rather sure that this is already being done. So the cycle goes like this. AV releases a signature update, and they do it, I don't know how often now, twice a day, 3 times a day. The bandwidth costs must be gigantic. So the malware authors, of course, subscribe to the AV engines. Having that subscription isn't all that expensive, really. And they notice our malware gets detected. They create a few duplicates of that file. Then they use the debug symbols to look up, hey, which functions do we need to change and recompile? And they do that, and they recompile, and they release, and the entire cycle took about half a day, and we have a new variant. And now the AV guys have to take that sample again and extract a new signature. It's a great business model for the AVs because they can make it very plausible to their users that they need to update the signatures all the time, and it doesn't really hurt the other side either. So when you have signatures for malware, you really do not want them to be brittle or local. Meaning, the true criteria that you want for a signature is you should be reasonably flexible when people start changing stuff, and you should cover most of the executable and not only a small part of it. All right, so yeah, there's a bunch of different methods for automated malware classification under consideration nowadays. It seems to be a rather popular topic. And there's in the whole about 4 research directions that I've seen, and I'll speak about the first 3 ones first, and then I'll speak a little bit about what we're doing. Before I start, I'll say one thing. The goal of a malware classification engine has to be that the malware authors cannot use the standard dev tools anymore. Right now they're using standard compilers and they're just recompiling with minor changes. we can't make malware detection like 100% reliable if we have a sophisticated attacker with enough resources. The goal really is to get the malware authors to have to do something clever, like not use just the compiler for polymorphism, but disassemble and mutate their own code again. The goal is not to have something perfect, the goal is to break the use of cheap tools. All right, so something that's very, very popular these days is behavioral classification. Behavioral classification, in essence, works by executing the malware in a sandbox and recording events as they occur, and then ordering these events into a sequence. And when you have a sequence of events, you can calculate the distance between two sequences by something called the Levenshtein distance. Levenshtein distance is a fancy word for how many insertions and swaps do I need in order to transform one sequence into another. And in essence, that's just what you do. You have these sequences, you calculate the Levenshtein distance, and you weigh the events with different weights. So some events affect the distance more than others. And then you sum it up and you get some sort of distance. Now, the problem with behavioral classification, well, I'll start with the pros first. The advantages of behavioral classification are you really don't care what, like over how many executables your malware is spread. You don't care whether it's spread over multiple processes. You just collect events system-wide and then start comparing. Secondly, behavior extraction is comparatively easy. The downside is you have to run the software and it has to be active in order to be observed. So if you're in a forensic situation where you find a rootkit on somebody's box, or a suspicious piece of kernel memory that is executable and that shouldn't be there, this really doesn't exhibit any behavior at that point, so you can't do anything with it. Secondly, a lot of malware, when you see it nowadays, just doesn't do anything for a significant portion of time before it actually starts doing something. So behavioral classification at that point is not going to be quite so successful. The biggest problem that I see, though, is that behavioral classification can be trivially fooled. I don't even need to recompile my executable. I can just randomize behavior a little bit, and out of a sudden, an executable is not even self-similar anymore. So these 5 lines of C code down here will essentially make an executable not self-similar. You just start the executable, you run it, and then you open and close random files for a while. And, well, each of these operations is going to be an event. And you have a random number of how often you do this, so out of a sudden, your two sequences are arbitrarily far away from each other with this distance, and you're running the same executable twice. So that doesn't quite fit the bill. A different approach is something called n-grams and n-perms. One question, is there a glass of water somewhere around? Right. Thank you. Apologies, I was invited to some drinking yesterday evening and I haven't quite recovered yet. All right, so n-grams and n-perms. Yeah, the idea behind n-grams and n-perms is you go through an executable and you count how many times an unordered sequence of instruction occurs. So, for example, you want to calculate the 5 perms or 5 instruction perms of an executable, which means you're looking at all possible permutations of all possible instructions of length 5, and then you count how often each one of these occurs in that executable, and then you get a very, very high dimensional vector with 1 dimension for each possible permutation of 5 instructions. Well, then you start comparing these vectors. And that actually works somewhat. The idea behind using this is, well, compilers rearrange instructions. So by not considering ordered sequences of instructions, but unordered sequences, we might actually be able to compare even though the compiler is reordering stuff. So, yeah, you go through the executable, you count how often these things occur. And the problem is that the dimension of that vector is so ridiculously large that you now have to come up with a clever way of comparing these things because the standard methods don't quite work that well. And what they're doing, in fact, is they're calculating the cosine angle between these two vectors. And that means, okay, we have these 2 very high dimensional vectors and we don't really know whether they're the same, and comparing them is stupidly expensive. So we'll just see, do they point in roughly the same direction? And then start working with that. Now the problem with this initially is that there's many very common code sequences that are generated all the time, function prologues and the like. These code sequences would lead to like a few entries in this vector dominating all others, and you're just recognizing, okay, this has been compiled and that has been compiled. So what they do is they filter out those sequences that occur a lot, in the sense of they divide that value in that vector by the number of executables that exhibit this feature. So in a way, things that occur very often will get normalized. And then you just calculate the cosine and see whether it's similar. Advantages, it's simple, it's fast, and it's not totally localized, so it does take the entire binary into account. The papers that I've published furthermore claims that it's resilient against code reordering and resilient against code motion, which I kind of dispute. The thing is that resilience against code motion breaks when you do this over longer sequences, because, well, you're looking at unordered sequences of instructions, and the compiler will reorder within that sequence of instructions within a basic block. But the compiler will also reorder basic blocks. So when you choose your n to be fairly large, and the compiler starts swapping basic blocks around, your resilience against code motion breaks. And surprisingly, or the average basic blocks are surprisingly short. Like the average basic block in our databases is between 4 and 7 instructions. So really, you are breaking as soon as you start being a little bit more expressive. Yeah, so this is kind of limited. It's also extremely non-resilient against different choices of mnemonics by the compiler. So if the compiler decides to replace, I don't know, a move with something else, then, well, clearly that will distort the results. And we're not even speaking about an attacker trying to be malicious yet. If I was malicious, and I wanted to break nperm's classification in my build process without actually having to do anything, I would insert something into my executable, which is an if condition that is always going to be false. And after this if condition, I'd call some function. And this function would never actually be called during the runtime of the executable. And I'd create an assembly file in which I put 10,000 times the same instruction. And then I compile and link the entire thing and release the bug, or release the virus. So what happens to this algorithm then? Well, we have 10,000 times the same instruction in a row. And we're counting all unordered sequences of instructions of a certain length. So I'd say we have 10,000 times knob. And then we count, okay, we have one occurrence of the sequence 5 knobs in a row at the first instruction. Hey, we have another occurrence of this at the second instruction, and so forth. So this instruction sequence that you've chosen for this piece of assembly code will just have a ludicrously high count because you're counting at every possible offset, right? So you'll have a value of 10,000 essentially, or 9,900 something in the vector for the 5, or in that entry for the 5 knobs. And this is an instruction, or an instruction sequence, that doesn't occur naturally. So it will not be normalized away. So that means that when you actually try to do the comparison thereafter, the stuff up here doesn't change at all, but one of the two down here is made very, very large, which means you decrease the similarity more and more. So in essence, you can build an automated build process which will emit to completely identical executables that are not similar at all by this measure if you just change the knob to an add. All right, so that stuff is kind of brittle. The next approach is something called basic block distance, and is done by people at Microsoft. What they do is they build a sort of hash function. So you have a hash function that takes a basic block, normalizes away the addresses, and then hashes it some way onto the numbers of 1 to m. And then you have a vector of m bits, and you go over an executable, and whenever a particular basic block, like you take every basic block and you hash it, and you set the entries in that vector to 1 if that basic block occurs, and leave it 0 if it doesn't. So you get a bit vector that represents the basic blocks in that executable. And the big advantage of this is it seems to scale surprisingly well. Like they're doing, like using this on really large quantities of executables. Trouble is though that building a decent hash function here is not easy. And secondly, especially building one that is resilient to compiler changes and to compiler optimization changes is really difficult. So yeah, unlike unless you manage to build a hash function that can deal with people reordering instructions and doing stuff, it's not going to be resilient towards compiler changes. But from what I've seen of all the three approaches, I think this one is the one that at least carries the most promise. So clearly, after bashing the competition, I'll go over to speaking about what we're doing. We do structural classification. The idea behind this is you take a program and you interpret it as a directed graph, and then you do the comparison based on that graph. And in essence, we want to build, or we're building something, well, we have built. I get confused with the time sometimes. So we built a system where you submit executables, and we try to automatically unpack them, remove the runtime encryption, disassemble the executable, generate flow graphs and call graphs from the executable, and then run a comparison algorithm that compares the structure of the executable with the structure of the other executables that we've classified beforehand. And those of you that have been doing patch analysis in recent years might know why and how we're doing this. And well, I'll begin to speak a little bit about the automated unpacking. The thing with automated unpacking is that in the worst case, unpacking can be made arbitrarily difficult by the attackers, but it does require some investment by them. And the usual approaches to unpacking are something like manual debugging and dumping of memory, which is terribly time consuming, and people will start playing silly tricks with your debugger. Most AV engines actually emulate an x86 CPU and a few of Microsoft's API calls, so that they can step through the packer and then be fine. The downside of this is that packers and malware authors have gone towards calling weirder and weirder Windows APIs and depending more and more on undocumented return values from these APIs. And clearly your AV engine is not emulating the undocumented return values correctly and then not properly decoding this. This was what Storm did and why a lot of the AV emulators failed on Storm. And then there's the other approach, which is writing packer-specific code for every packer. Problem is you need a building full of reverse engineers to do that, and some people might be able to afford it. We can't. Our solution to this was we'd like to have debugging, but in God mode, like no anti-debugging, please. So what did we do? We took a full x86 emulator and we modified it so we had Python bindings and callbacks on every instruction fetch. And then we installed Windows in that emulator, which is a bit painful because installing Windows XP into a slowly emulated environment does take some time. The advantage is that you don't need to care about emulating APIs because you are running Windows. You're running Windows slowly, but you are running Windows. And there is no debugging, hence there is no anti-debugging. And somebody will then think about some anti-emulation tricks at some point, at which point we will be able to deal with that by just running the trace in the emulator once and running the same trace in a hardware ICE and then seeing where the two instruction flows deviate, and then you see where they're playing tricks with your emulator. You fix your emulator and their trick is gone. So I'm quite confident that that'll work fine. And we have another advantage. We really do not need a full reconstruction of the binary for unpacking. We just need a significant quantity of memory, well, a somewhat significant quantity of memory, where we can extract decent disassembly from. And what we do for unpacking is we really just take the executable, we emulate it for a few million steps, and then we take repeated snapshots of memory, and whenever the memory starts looking nice, we start disassembling it, and then we take the nicest snapshot that we made and work with that. So I have a bunch of slides on how the actual comparison algorithm works, but I've given many talks over the years over this algorithm, or about this algorithm. Should I speak about this, or should I skip the next 15 slides and go to the other stuff? Who here would like to hear about the comparison algorithm? Raise your hand. All right. Okay, so yeah, the idea is you take the executable and you disassemble it, and the executable itself is a graph of graphs then. What do I mean with a graph of graphs? You have a call graph, which means you have the graph that consists of all the functions and how they call each other. And every function itself is a flow graph, because you have the basic blocks and how they relate to each other. So now you have a big graph, and every node in that big graph is a small graph. And now the idea is that you want to compare the program based on this structure. So we have a call graph here of some piece of malware, I think it's MyDoom. And we have some flow graph here, just as a visual illustration of what I'm talking about. And the thing that's cool about these graphs is that the program logic is encoded to a certain extent into these graphs. So if you change a call from string copy to strn copy, you change the call graph. And if you add an if into some function, you change the flow graph of that function. So in a way, the graphs are the shadow of the program's semantics. So you have the program up here, and clearly we can't analyze the semantics properly, but the compiler will encode these semantics into these graphs, and we get these graphs. And that is at least something that we can work with. The nice thing also is that most compiler optimizations leave the core graph invariant, meaning almost all compiler optimizations up until 2 years ago or so would not change the core graph. They would work on the function level only. And even now, with something called whole program optimization, the core graph stays largely the same. Not completely the same, but largely the same. So a comparison of programs through the structure of the graph should be resilient to compiler changes, but at the same time cover the entire executable and be able to, well, see these parts of the executable we've seen over here. Okay, well, the advantage of this is it's neither localized nor brittle. The disadvantage is you need disassembly. And in the world of malware, where people are thinking that they have 60,000 new samples a day, disassembly is comparatively expensive as an operation. So whatever we're doing here, it's not something that you'll be running on your own laptop just because you need to have an emulator for unpacking. That takes some time, and then you need to disassemble, and then you need to run a large number of heavy computations on a bunch of graphs. Now, a different question is, how can we compare two graphs efficiently? And the mathematician will tell you that like comparing two undirected general graphs is NP hard, so that's going to be expensive. We are in the lucky situation, though, that we don't have general undirected graphs. We have very specialized, highly structured, directed graphs with a lot of extra information. The trouble, though, is we don't want to have a yes-no answer. Yes, these graphs are the same. No, these graphs are not the same. We want to have some sort of approximation. We want to have something, hey, we know these graphs are not completely the same. Please build me the best mapping between these two graphs that respects the structure of the graph. So in essence, you want to build, in math speak, like a graph homomorphism that covers most of the graph. Right? So what do we mean with something that respects the structure? Well, it shouldn't matter whether you first have a node k and then look at, well, map it over to the other executable, to the other node to which it belongs, and then consider its children, or whether you first take k, go to its children, and then map them over to the other side. So in essence, it shouldn't matter whether you go here or here. In essence, you want to have a sort of commutative, well, yeah, whatever. So how can we build such a mapping? The way that we build this mapping is that you take a function and you assign a 3-tuple of numbers to that function. You can take an arbitrary graph invariant, but in the old days we used the 3-tuple of numbers. And that 3-tuple was the number of basic blocks in that function, the number of edges in the flow graph of the function, and the number of subfunction calls. And what you do then is you have these two big bags of, well, nodes with 3 numbers on them, or 3 big bags of 3 tuples of numbers, and you associate those with each other that are unique on both sides. So if I have a node here, and this value occurs once and only once on the left side, and once and only once on the right side, I say these two functions are going to be the same. Yeah, and through this step, you can associate a few functions, not many, because the graph invariant that we've taken is very lossy. There's many graphs which have the same invariant here. So after you've created a bunch of them on a global level, you try to make use of the graph structure, because as of now, we've really just looked at the nodes as a set, right? So you now try to make use of the graph structure and look at the neighborhood of those nodes that you've associated. So, for example, in this picture here, the blue nodes we have no idea about. The red nodes we have successfully associated because this signature here is unique on the left side and on the right side. So we know this belongs to this. This is the same as this. And now we consider only the neighborhood of this node, and the neighborhood consists only of these two nodes. And out of a sudden, this signature up here, which was not unique and occurred multiple times in the entire graph, only occurs once in the immediate neighborhood of a node. So what you do is you create a few points that you know are the same, and then you improve from them. Like you incrementally build a better and better mapping from them. So because these signatures are now unique, you associate the nodes, and you examine the neighborhood of this node, and you associate the nodes in the neighborhood, and now you're almost done. Meaning you can now go through the neighborhood of this one and associate that node, and so forth. So in essence, you start with a very, very rough set of nodes that you know are the same, and then you improve your mapping step by step. And you end up with something that could be qualified as an intersection operator between binaries, meaning it tells you what is the same between those two. By implication, it tells you also what is different between those two, and that has been of great use and lots of fun in the vulnerability analysis business. Now the question is, what do you do with an intersection operator? For malware analysis and classification, you want something like a similarity measure, but strictly speaking, you have something more powerful. An intersection operator is a lot more expressive. And we had to build ourselves some sort of similarity measure from the intersection operator, because, well, we are not very good at stuff like generating family trees, so we couldn't really come up with an algorithm on how to create family trees from intersections. And we wanted to steal the ideas of the bioinformatics crowd, and they operate on similarities. So how do you build yourself a similarity measure from an intersection? That is not totally trivial in the sense of, well, the obvious idea clearly is you take just the size of the intersection divided by the size of one executable. That might be a possibility. But the trouble here is that you might have contains relationships. So in this case, it's relatively clear that we have this intersection here, and that has a relative size relative to the whole executable, so you can estimate what the similarity would be. But we have differences in sizes, and we have differences in how much these two executables overlap. So we have essentially not a symmetry here. How similar are these two? I don't know. Well, even these two. Now, if you consider the intersection here, the intersection is equal to the size of the small executable. So for the small executable is 100% similar to the bigger one, but the bigger one is not 100% similar to the smaller one. So, because we really couldn't get a clear idea on how to do this, we just invented something that half works and that is really stupid. The idea is that you calculate these similarities of this intersection on the call graph level, on the function level, and on the instruction level. And then you have essentially, well, you divide these values by the size of the executable as a whole. And then you have 3 similarities for each executable. And you just average them, and then you get 3 values of similarity. And then you average that with a given weight, giving more weight to the call graph than to the instructions, and you're done. And it's a very, very experimental physics style work, which means, well, this might work. So it's really not exact at that point. The advantage is that if you have an infinitely large executable and an infinitely small one, which is completely contained in the big one, you still get 50% similarity, whether you want it or not. Okay, so the other thing is scalability. We had to come up with a way of running our algorithm in essentially linear time, which we've managed to do, which is good. The algorithm in the end runs in about O(n) times m, where m is the average size of an executable, in functions, which is usually less than 1,000. That is a very approximate version of the algorithm. We then, after running an approximate version of the algorithm, run a more detailed analysis on those samples that were deemed interesting by the first run. So we really have a very approximate similarity, and then we take the most similar ones and run a detailed analysis. And the other way of making this thing perform better is discarding clones. A lot of executables will not actually be changed a lot, in the sense of, you will see, well, the AV industry will tell you that they see a gazillion new samples a day. Usually they kick around numbers like 60,000 unique samples a week or something like this. And they actually believe that these are unique programs. And somebody is not making the calculation that in order for there to exist 60,000 new pieces of malware a week, we would have to have several countries doing nothing else. And those wouldn't be small countries, right? So you know in advance that most of the samples you'll see will be minor And when I say minor, I mean minor variants of other executables. So what we do is, we just keep the most relevant ones. You send in 25 samples, and when a new sample comes in, and it is extremely close to an old one, you just discard it. And only if it is similar to an old one, but sufficiently different to warrant being kept as a new specimen, you keep it. So that's the entire idea. So the result is that what's eating our computing time now is the emulation and the unpacking. It's not really the classification. All right. Entire system has been parallelized except the classification. And this is what the architecture looks like. So you have an XML RPC server up on the front, and a SQL database from which into which it dumps the samples and from which it retrieves the results. And then you have a bunch of unpacking subsystems which fetch executables from the database, unpack them, drop the results back in. You have a disassembly and an analysis subsystem which disassembles and extracts the flow graphs. And then you have a classification subsystem, and those really operate independently from each other. All right. And now I'll show a little bit about what the system does. Okay, so this is the working list of the system while it's running. We're dropping files in there from a German students group called MW-Collect, or a German project by Georg Wicharski. They're collecting malware, and we're taking, we've been supplied the malware by them, and we drop them into our classification system, and it gets classified there. And yeah, so what do we have here? We have a bunch of executables, and we have family trees that we can generate from these executables. And they look a little bit ugly because a lot of the samples that we get from MW-Collect are very, very similar to each other. So you get many nigh clones, almost exact clones of one executable that have different hashes, but their similarity was somewhere clearly above 95%. So you have ugly executable hash here, and you have a ton of clones here. And in order to make the graph more clear, we can just hide all the clones, and the entire picture becomes a lot more clear. And then we see that we're dealing with actually a much more manageable number of real variants, and even these variants are comparatively similar. This number here indicates the percentage similarity between the samples. So you have these two samples here, and they are 89% similar. So they were just dissimilar enough to not be classified as a clone, and so forth. But all these are just hashes. I've uploaded a few samples that you might know. We've uploaded a bunch of stormworms, and they've been classified nicely together, which was quite surprising to us. Yeah, this system is a lot of fun. Also, we had a really, really interesting incident where, let me flip over, a customer found, had a crash dump with some code from kernel memory in it, and we then investigated and found this driver on his hard disk, which wasn't supposed to be there. And we uploaded the driver to the system as well, and it was, interestingly enough, it had a very small but significant similarity of like 20% or 15% to some bot sample that we had seen. And that was a little bit strange. Why would a driver have a similarity to a bot? And so the first thing we thought was our system must be flawed. So we downloaded the IDBs, like the system produces disassembly files for IDA that you can download, so you upload the executable, and then after it's unpacked and disassembled, you can download the IDB. So we download the IDB and ran bindiff on it, and what's causing the similarity is, amongst other things, this function here. And when we see all these red lines here, that means that the instructions changed quite a bit, but the actual flow graph looks remarkably similar. So let's have a look at the instructions. For example, at this basic block. Now, for those of you that do read assembly, what do you see? Somebody was inserting. Yeah, essentially, it's the same code. So somebody's just inserting garbage into existing code streams. Well, this pushes a value on the stack. It overrides, like it pushes a register on the stack, it overrides the register, and then it restores the register again. So somebody's just automatically going through his code, and whenever he has like 2 or 3 instructions in a row, is inserting do-nothing garbage. And that was quite surprising, and it was nice that we caught it, and I'm quite happy about it. Yeah, so that was this. Back to the slides. So this is what we're doing now. Where is this entire classification game headed? Predictions are usually really, really difficult, so don't call me on these things in a few years. You can easily attack the system, but I think 5 minutes? Okay. You can easily attack the system, but I think you might have to change your build environment quite a bit for it. Let's imagine a future where you don't have self-modifying code anymore. In the long run, I think what will happen is that Microsoft will outlaw self-modifying code. So what will they do then? How can they continue obfuscating that code in the future? And in essence, I see two avenues that they'll be pursuing. The one is insertion of, yeah?
So just keep writing more code.
That might be true. All right. So one of the things that I think will happen in the sense of obfuscation is insertion of opaque predicates, which means inserting a lot of conditions that are false, but it's not easily discernible whether they're true or false. I'll explain that in a minute. And the other thing that we're seeing a lot are emulating packers, where they take an entire executable, transform it into an intermediate language, and then emulate that intermediate language instead of actually running the code, which is somewhat annoying. Takes time to take apart. So opaque predicates. Well, clearly if you wanted to attack this, you would want your flow graphs to be dissimilar on every new rebuild. So for this, what you could do is you could insert a lot of unconditional jumps. That's what they are already doing in order to confuse people. Unconditional jumps are being optimized away when we generate the flow graph, so we don't really care about them. In order for them to do something clever, they would have to insert conditional jumps, but in a way that it is not evident that these jumps are true or false. Because you don't want somebody else to just run an optimizer on the code and have all the conditions that you built just drop away. Thing is that there's academic research into opaque predicates. Trouble is that all things that they've come up with so far are number theoretic. So you can do something like, hey, we have an opaque predicate here, you can't tell which way this branch will go. You just have to do a modular exponentiation a few times. And clearly it's not an option to add a modular exponentiation into 25 places in your function and still have the program run in reasonable time. Yeah, so that's one thing. The other thing is emulating packers. They're really annoying. And the one thing that we are trying to work on at the moment is at least looking at the public implementations that exist and generating disassemblers for the intermediate language, and then just comparing the flow graphs generated from the intermediate language to the flow graphs generated from another intermediate, like from another run of the same program, or of another mutation of that program, because the flow graphs remain mostly the same. We've diffed ComWarrior on ARM, and ComWarrior and ARM thumb, like ComWarrior A and ComWarrior B, are compiled for essentially different instruction sets. And the structure of the program stays largely the same, so I think when we can extract that stuff, we should be fine as well. Yeah, that's pretty much it. If you have questions or anything, ask them now. If you want to send us malware to classify, you can drop them in a passworded zip file with password infected to vxclass.submit@dynamics.com. We will most likely, like, I don't give any guarantees of this getting back to you in reasonable time, because it's really just, if you drop us malware and we happen to have spare cycles on our computers, we'll run the classification. There's no guarantee that you'll get an answer, but I'll promise you we'll try to run the system at least once a week on customer submitted or people submitted stuff. All right, any questions? Come on, Dave. Oh, sorry. Actually, the question was back there, I think. Sorry.
I just wonder about the algorithm you were talking about. Doesn't it cause you a lot of problems if executable has been packed with some sort of crypter that is publicly available on the web? Because if you have several variants of different bots that could be crypted with one packer, you get the similarities for the packer and not for the bot itself.
Well, the similarities for the packers will occur in the calculation if you do it naively. But we already filter out, like the other problem that you have is statically linked libraries from compilers. So before we actually calculate the similarity, we filter out code that we've seen, which means we have a library of code that just doesn't get taken into account. So if they have a packer that is that we haven't seen yet, and they pack the executable 55 times with it, then clearly you will see some drop in the similarity, but it can't drop below 50% really if it's wholly contained in another executable. So, like if the core executable is, well, it can drop below 50, but you can't make it arbitrarily small because you'll have the core application still be matched to the core application somewhere else, even if you add layers and layers of packing.
Yeah.
All right, if there's no questions, thanks. Oh, sorry. Sorry, that's... I hate to interrupt your applause, but...
Just a last minute question. How does this relate to, let's say, the actual detection on, let's say, the client systems? Because if I understood it correctly, this is, let's say, a much larger system where you identify this. Is there a link also to the client environment?
Well, the link to the client environment is rather something, let's say you do forensics in an enterprise, and you find a certain bot on, or a certain suspicious executable or piece of memory on one box. Then you submit it to the system, and the system tells you, hey, this particular piece of code is bad, or is at least similar to something that is bad. So what you can do then is you can scan for that particular file over all your systems and see where else the infections are. And we're currently working on, given a family of executables, optimizing, well, generating a signature that catches all members of that family. The background for this is, in the end, we are a business and we're trying to sell something, and the antivirus companies are very reluctant to actually change their way of working, and they have huge bandwidth fees. So from sending signature updates all the time. So when we can't, like, if we can't make them use our classification, we're building something right now that, well, given a set of executables that have been classified, generates the smallest possible signature that catches everything that was in that family. So we're trying to optimize existing AV signatures by size in the hope that AV companies will pay us for optimizing their signatures because they're saving money on bandwidth. The hope is you go up to them and you go, hey, folks, you don't need to change anything you're doing. We'll just start saving you money tomorrow. And we hope they will go for that. On the other hand, the core idea really is you submit a file, you see whether it's interesting or not, and then you can look for the file elsewhere on the other systems. Right. Any more questions? Yeah.
Wait, please.
Fair enough. Right, thanks.
Well, if there's no more questions, thank you very much, Halvar, for your talk.